I don't know why, but maybe the reason why tensor product was not defined as early as in 19th century is because the paradigm changed during the middle of 20th century towards categories from sets. So the foundation of math is now more based on categories than before. And the notion of tensor product is sort of categorical. So today I will try to explain how it works. And so most of the talk will be about categories and how to work with them. There was something I already has mentioned when we discussed the equivalence of categories, namely natural transformations of functors. And so the idea is that functors themselves form a category, and natural transformation of functors are morphisms. The object of this category are functors, and morphisms are natural transformations of functors. So let's define it. And then equivalence will be an isomorphism in that category. So you have f and g, two functors from category to another category. And natural transformation of functors is morphism from, so for each x, for each x inside the objects of C1, define morphism denoted by psi x. It will be a morphism from f of x to g of x. So it is a morphism in category C2. And we want this to be compatible with these functors in the following sense, that if you have f of x and also, sorry, in addition to that, you have, let's write, before I write this diagram, let's write that formally. So for such that for each phi inside morphism from x to y, so you can take f of phi, which will be a morphism from f of x to f of y, and take its composition with psi y, which is a map from f of y to g of y. And this should be equal to psi x, which is a morphism from f of x to f of y, times g of phi. And now I'm going to draw a diagram. So you have f of x and psi x maps f of x to g of x. Here you have map morphism, which is associated to phi. So it's g of phi. It's a map to g, since phi is morphism from x to y, so g of phi is a morphism from g of x to g of y. Here we have psi of y, here we have f of y, and here we have f of phi. This should be commutative. So commutative diagram is a diagram where you can go this way or you can go this way, and the compositions are equal. So this is a natural transform of functors. Clearly, if you have two natural transforms from the functor, say f to g, and then you have g to h, and you have this transform. This was psi x, and then you have another transform which you can consider phi x and phi y, where phi is a transform from g to h, natural transform from g to h. Then the commutativity of this diagram plus commutativity of that diagram implies the commutativity of this diagram. And this implies that composition of natural transforms are natural transforms, and clearly the identity, just identity map from functor to itself will work as identity in that category. So indeed, I mean, this is a category because you have the identity, you have morphisms, you have composition, which is associative. Okay, so we had that part of it at least, because when I defined equivalence of categories, I just had the same notion, except that in that case, all these morphisms were equivalences, were isomorphisms, and we needed to have a functor which has inverse. This was for equivalence, but now we don't need equivalence anymore. We just have any natural transform of functors. Okay. So category theory seems on the surface completely that it looks like it has no content. And this, in a sense, it's true. So many people call category abstract nonsense. On the other hand, using categories, you can define pretty much everything in algebra and geometry, just using internal tools of category theory. And the main tool is these representable functors and any other lemma, which will be in the next slide. For instance, today I will explain how you can define products or coproducts, which is like amalgamated products in group theory, using purely categorical notions. And in fact, this helps to prove the theorem I stated last time and proved algebraically. Well, I proved it by using the ideals and Hilbert-Neustein-Satz, but now you will see how to prove it without any high-level math, but just categories. Okay, so so this is abstract, but it's useful. So we have two kinds of representable functors. So definition, a functor HA, it's a functor from C to sets, to category of sets, is called representable or represented by A inside the object, so it's an object of C. If HA of X is a map from, is morphisms. Morphisms are a set from A to X. We want it to be covariant. This is covariant functor. The contravariant functor can be also called representable if you write it in the opposite order. So a contravariant, well, let's postpone contravariant functors until the next slide. Okay, the important thing about covariant, well, about functors to sets and representable functors to sets is that the functor uniquely determines the object which you use to define this functor. Before that, I explained that, let me just state the claim of, which is like a preliminary statement before any other lemma. So claim. So I consider a functor f to sets and a natural transformation of functors from HA to N. So I have f from C to sets, and HA, also from C to sets, are functors to sets. Sets. And phi is the natural transformation of functors from HA to F. Is a natural transformation. Then this natural transformation phi is uniquely determined by an element f of identity on A. Which, phi of identity of A. Which we consider as an element in f of A. Let me explain. So identity of an A is a map from A to A. So it's a remark. So identity in A is a morphism from A to A. So it belongs to, it's an element of the set HA of A. And then the natural transforms, they map, these are morphisms in the category, which is the second category. Here is C2, but in our case it's sets. So f, the phi is a map from HA of A, phi A, to f of A. And we take identity, which we consider as an element there, and take its image. So the claim is that this image uniquely determines, and in fact there's just one-to-one correspondence between these images and natural transforms of this type. Okay. So this is the diagram which represents natural transforms. So you have object f of g and g, f of x and g of x, f of y and g of y, and you have these morphisms, and you have commutativity of this square diagram. so I'm going to give you the proof. So for any lambda inside morphism from A to B, so both A and B are objects in C1. We have a commutative diagram which is standard, which is the same commutative diagram as here. So you have HA of A, which is the same as morphisms. It's a set morphisms from A to A. And we can consider the composition map F goes to F composed with lambda. This would give previous morphism from A to B, which is the same as H A of B. Now we apply our natural transform, which I denote by phi A, and it goes to F of A. And this goes to F of B. And here we have F of lambda. So this is commutative. Okay. So now we assume that this arrow so it takes the top arrow, takes identity to lambda. This is what we have actually if we write everything as it's written there. So this implies phi b of lambda. This is equal to f of lambda, this arrow. And then we take we compose it with fa of identity. Well, we take this and that. And this implies that phi b, it's a map from morphisms from A to B, from this to f of b, is equal. So we obtain that phi b is equal to phi a of identity. Well, sorry, it's f of lambda applied to phi a of identity. Okay. So this allows to recover f of b if we know phi a of identity. So,
Can you repeat the last one? No, not this one.
so again, so look what we obtained here. We obtained that phi b of lambda, this map. So we have an element here, and we have its image there. This is what we need. I mean, for each a of b, for each lambda, we have this this map. So we're interested in what is, and we know that phi b, this map, is equal to phi a of identity times this. So from commutativity of this diagram, it follows that if we know this, so this we know for free. And if we know this element, which is we apply phi a to identity, we know this, we know this, then this again identity, so we know that we know this. Maybe I should repeat this again, because it's tautology, it's so simple, it's incredibly hard to understand because it's that simple. This is paradoxical result of something which is entirely tautology. So we want to prove that for any lambda, well, we want to prove that if we know the image of identity, we can recover our transformation of functors. So we start with identity. We apply to identity, we obtain f of a. Now we are interested in what does this functor do? What does this map do? This is a map from finite set to finite set. But, however, every element of that, every element of here is an image of identity, which is obtained by taking composition with morphism from there. So we take as lambda our morphism, our element in that set, and we consider a vertical arrow lambda, which is given by that element. So we can take any element, any morphism from A to B, and with any morphism from A to B, we can associate it this kind of square diagram, which will be commutative. So we take as a lambda, we take. So we start with some element. Here we take lambda as its image. So we just consider, we take lambda there, and then we take vertical arrow, which corresponds to lambda, because every element is a composition of identity here and some map for some morphism from A to B. So the vertical arrow is lambda. The horizontal arrow is f of lambda. And f of lambda is uniquely determined by lambda. So we start with an element here. We reconstruct the whole diagram. And if we know that, we know this. Because this and that is already determined by the choice of lambda in there. So we obtain that this map is uniquely determined if we know this. Conversely, if we know this image, you can always start with lambda there, write this diagram, and this will give you a map from there to there by doing this comparison. So there is a bijective correspondence between natural transforms from HA to F and elements of this set. So natural transforms from HA to F are in bijective correspondence with the set f of A. I can repeat this argument again if it's not entirely clear. Should I? Clear? It's straightforward. It's tautology. Sorry? No, but maybe we can discuss this. It's tautology, but it is really hard to understand tautology. So it's perverse. So again, you start with, we want to know what is an element. You start with lambda here, we want its image there. How we do that? We consider the diagram which is associated with this lambda. So we consider lambda as a map from there to there. This is how you do that. You just start with identity, and you put the lambda, which is a map from A to B, and then the image of identity will be your lambda there. So it's an image of identity from here associated with the arrow, which is lambda. Here you have f of lambda. So lambda is a morphism from A to B, but it gives you a map from H of A to H of B, because H is functorial, and this is precisely the functor, the image of this morphism under this functor. It's just composition of, we start with, yeah, it's a composition. So here you have a map which is composition with lambda. You do it with identity. So you know the image of lambda from here to there. Because if we know the image of identity, then you apply identity from that map to this map. You obtain the image of lambda will give you the image of lambda there. But then here you can start with identity and you apply f of lambda to its image. So this implies that phi of B applied to lambda is equal to f of lambda f of lambda applied to this point here. F A of identity in A is an element in that set. And f of lambda applied to this element is this. F of lambda doesn't depend on the choice of natural transform. It's given, it's like fixed in stone because it depends only on f. So if you start with a lambda, which is also independent, and you run this diagram, if you know the image of identity there, this allows you to reconstruct image of lambda there. And this is unique. So whatever map, I mean, if you know what is the image of identity from here to there, this gives you immediately by this running this diagram, this gives you immediately a natural transform. Okay. So this is one of the forms of Ioannina lemma. So it's bijective correspondence between the natural transforms and image of A. So this corollary is in fact Ioannina lemma. Yeah, so it tells you that if you have a map from this set HA to f of A, it gives you natural transform, and of course, if you have a natural transform, the image of identity is given. But it uniquely determines the rest. Okay. Now I'm going to give the category of functors from so for present purposes, I need to define category of functors from two sets, though you can do it with any two categories. So the object of this category is functors, and the morphisms are natural transforms. So define, well, I already defined that, so I should probably just use some introduced notation. So remark. So suppose that, is there any notation for that? There should be. Yeah. So consider the category F tilde of all functors from C to Z. And F inside it, all representable functors. And you have a contravariant functor now from C. Consider a contravariant functor from F. Since it's contravariant, I use a circle to indicate that it's opposite category to sets, which takes A to HA. So why it is contravariant? This is because if you take a map from so we're interested in maps from H to X, from A to X, and if you have a map from A1 to say X, then, and you have a map from A1 to X, then this gives you, then every map from A to X it can be composed with this, giving you a map from A1 to X. So it is opposite to if you have a map from A. So if you have phi from A1 to X, to A, sorry, to A, this then each phi is a morphism from. So I take a composition. This gives you from H A to H1 A1, because you take a composition from of this arrow with that arrow. So it's a contravariant functor. So corollary. Which is also a Ioannidis lemma, and this is the most important version of it. That this functor F0 to sets, sorry, it's I wrote two sets, but in fact it's sorry. It's of course it's not two sets. It's from C0 to F. It's A goes to HA. So it takes an object in the category and produces a representable functor, representable by this object. C0 to F is an equivalence of categories. So the point is that if you have a two objects, because natural transforms, so it's morphism from HA to HB is the same by this result as HB of A, which is the same as morphisms from B to A. So it acts bijectively on morphisms, on objects, on classes of isomorphism of objects. So it maps, if you have two equivalent objects, they give you two equivalent, two isomorphic objects, they give you equivalent functors. And conversely, if you have two functors which are equal, they produce you, they're given by equivalent objects. Well, you can also think about this as follows. You have a map from here to there. It is bijective on isomorphism class O objects, and it is bijective on morphisms. So it is bijective on morphism by this argument. But then to see that isomorphic functors give you isomorphic objects, you just obtain identity as an image. And you can, if you have two functors which are given by you have two objects which give you equivalent functors, you can just put identity there, because then the identity there, this will be map identity there. It will be identity from here to there, and this give you morphism which is invertible, because I mean, this is an isomorphism, then this is can be composed with the opposite morphism from HB to HA by giving you, and it will give you identity map from A to A. So this is why you can always reconstruct an object of category from the corresponding representable functor, because this is an equivalence of categories. Okay. Now, yeah, so contravariancy becomes important because it's a way you so if you want to have the functor HA covariant, then it will depend contravariantly on an object of a group, and conversely you can consider the opposite. So you can state the same result, but for contravariant functors. You consider functors not morphisms from A to something, but morphisms from something to A. This is a contravariant functor to sets, and it will give you a covariant equivalence between category and representable category of representable functors, covariant functors. Oh, sorry, contravariant functors to sets will give you covariant equivalence between category of your category and category of representable functors. This is Aneda. Aneda was a graduate student who was tasked with accompanying Ellenberg through Japan, because at the time, of course, it was 40s or very early 50s. Nobody in Japan has spoken any English, so it was very hard to orient. And then after Eulenberg returned to United States, to Chicago, Aneda went with him and became a graduate student. And then at some point he was already a graduate student, but he worked with him a lot and with McLean. And then he returned to Japan and became a computer scientist, mostly because his superiors told him to be a computer scientist, and they disregarded the category theory. So then he was, I think, like a Japanese president of the Algol 68 committee for the language of Algol 68. And he didn't do much math since he returned to Japan. Okay, there's another way of looking at that, because so instead of using the language of representable functors, you can use language of initial and terminal objects, and this is something we have discussed. So, yeah, the diagram in category is just a graph. So, suppose you have an oriented graph. This is a combinatorial object, which has so far nothing to do with category. But we can put objects of category in vertices. So let gamma be a oriented graph. So you have point, vertex, then you have arrow. Oriented means that all edges have arrows, they're directed. So it's directed graph. Now you can have anything. It's not important what kind of combinatorial structure you put. And then suppose you have for each vertex, we have an object, fix an object. A inside the object of the category, and for each edge, we fix a morphism, between objects in vertices. So here you can put A, B, C, D. And since the edges are oriented, they have arrows, we have always a direction where of this morphism. So this is called a diagram in category. This is a diagram in category. So I'm going to define limits of categories, in categories, and this is a language which actually precedes the language used by Aneda. It's equivalent, but in a sense, sometimes it's simpler, sometimes it's harder, but it's also very useful. It's an equivalent language which can be used alternatively with Aneda. Okay, now diagram is commutative. So it was definition, and this was definition. Diagram is commutative if for any, so you have two ways of going from one vertex to another. Two ways of connecting two vertices with arrows, oriented arrows, obviously. The corresponding morphisms have the same compositions. So in this picture you have, you start with A, all arrows start with A. I mean, there are arrows which start with D, but there are three arrows which starting with A, and they lead to D, or lead to B, and then lead to D. So you need this to be, this triangle to be commutative, and you need this triangle to be commutative for the whole diagram to be commutative. So I'm going to define limits. I'm going to define them for commutative diagrams, though you can easily do it without commutativity. Just apply your imagination and you will see. Okay. So you have a diagram. You can associate it with the diagram category of pairs. So suppose that D is a diagram. And you have a category, and CD is category of pairs. X inside the objects of our original category, which we start from. So the diagram D is a category in C. A category of fixed diagrams. You fix diagram and you consider it's like a representation of the diagram in C. And then phi I from X to Xi, where Xi are vertices. Are vertices of our diagram D, such that everything is commutes. So if the arrows are called so vertex fix this object, let's call them xi, and the morphisms are called phi ij from xi to xj. So this is our morphisms, like in that diagram. Are vertices of this, such that the diagram formed by x, xi, phi I, phi ij is commutative. So here's the picture. This was a triangle. This was our diagram. And then we added x. We considered lots of arrows from x to this to the vertices of the diagram, and we want the whole thing to be commutative. So there are lots of triangles which has to be commutative. These are objects of this category. So morphisms of this category are x and x prime phi. So you have x with all phi I. This is one object, so it's an object of category plus maps to all vertices of our diagram. And you map it, you are interested in morphisms to x prime phi I prime are elements of the morphism from x to x prime, such that the whole thing is commutative. So you take diagram formed by x, x prime, xi, and then phi I prime, and phi ij is commutative. So it's like this huge diagram in this picture. I'm not going to make it on the blackboard because it will be entirely unreadable. So you have two elements, x and x prime. Here it's in opposite order. And then you have lots of arrows to the xi's, and you need to have the whole thing commutative. So it's a whole, there are lots of loops in that graph which lead you to the same objects, and they all should commute. Okay, so limit, definition, limit of the diagram. Typically it's infinite, but not always, is the terminal object in that category. So it's terminal object in CD. What is terminal? That is an object such that for each element, for each object, say A in these objects of CD, there exists a unique map, morphism. So it exists unique, say, phi, doesn't matter, inside morphisms from this A to this terminal object. This is something we have discussed. So let me give you an example, which is one of the example of the examples of the limit. So we take a diagram of sets, say embeddings. So it's an you have x1 goes to x2, goes to x3, and so on. And suppose they're all embeddings. And you can instead of to positive and to negative as whatever you like. They are sets. So now you are interested in maps from A to these guys, which commute. So this, since this all embedding, this means if you have an this means that you have a map from A to in the intersection of all xi. These are all injective maps, and then you have a map from A to these sets. They commute. So this means that each of them is injecting, and this, well, maybe not injection, but what is important, they all arrive to intersection. So it's a map from A to intersection. And in fact, the limit will be intersection. So limit of this diagram is intersection of xi. This is because if you have a map to the intersection, if A is mapped to intersection, then it's mapped to intersection. This is unique. So if you have any map to this diagram, it's factorized through this intersection. This factorization is unique because all these guys are embedded into each other. This was limits. Co-limits are the same, but you have to invert arrows. So if you have map from A to the diagram, it's limits. If you have maps from the diagram to A, this is co-limit. Let me give an example of co-limit.
Why this intersection?
Sorry?
Why this intersection do not coincide with x0?
Because we have x minus 1 here. Yeah, it's infinite. Of course, if it were, if it was started from x1, I just didn't have space. Thank you. It was important, yes. So let's do another diagram. You know, it could be infinite in both directions. Doesn't matter.
What it has either limit and co-limit?
Sorry? I'm going to define co-limit, yeah. I defined it. I'm going to explain what is co-limit of this diagram. So now again we have x0. Here we have embedded x minus 1. This embedded to x1, x2. But instead of having maps from an object to this, from the set to this sets, we are interested in the opposite maps, like from this to A. And this, again, everything commutes. So this means that we have a map from the union of all xi to A. Because all these guys are embedded and all they are mapped to A. And conversely, if you have any such map, it gives you a map from the union. So the union is initial object. Yeah, so for when you speak of terminal objects for limits, for opposite category, it should give you initial object. So co-limit is the initial object in the category, but where you take maps from the diagram and not to from the diagram to X and not from X to the diagram. It's like the same notion, but in opposite category. Okay, so the limit. So inverse limit is, or limit, it's where you write the arrow the opposite direction. It's also called projective limit. And this is injective limit. You write it there, all core limit. And it will give you a union of xi. You can do the same with vector spaces, and it will give you again the limit. But what is probably more interesting is that you can obtain periodic numbers as limits. If you know what is periodics, then you can easily prove that lim inverse of z by Pn z is Zp. Where here you have diagram 0 goes to z by p, goes to z by p square, and so on. It's a group diagram, and periodics are obtained as inverse limit, and that's set up. If you don't know what periodics are, it doesn't matter. You're not going to use it. Yeah. In fact, today I will use only, I'm interested only in finite limits.
Here the maps are surjective.
Yeah, there's quotient maps which are surjective, yeah. So, but you should think of limits as unions and inverse limit as intersections. This is somehow the most convenient way of imagining this strange guys. So another important application of the limits is the ring of germs of functions. So consider, so let's M be a smooth or complex holomorphic or whatever. Let's smooth manifold. And then you have x inside M. And you are interested in functions u f1 and f2 defined in a neighborhood u1, u2 of x. And we call them equivalent in a neighborhood, like they have the same germ. So f1 has same germ as f2 if there exists a smaller neighborhood u inside u1 intersected with u2 such that f restricted to u is equal to f1 restricted to u is equal to f2 restricted to u. And we're interested in, so germs are equivalence classes of functions in X are the same as equivalence classes of functions under this equivalence relation. So I claim that we have the following diagram. So diagram, it's open vertices are open set containing X, open sets in this set M, smooth manifold, in M containing X, and arrows are just tautological open embeddings.
The diagram may not be countable.
Yeah. It won't be countable unless you add some extra condition, but it doesn't really matter. You can make it countable, the answer will be still the same. So now for this diagram, you have you have corresponding diagram in the category of rings. So you have U1 sits in U3. Here you have U2, it sits in U3, you have U0, which sits there, and so on. So there are lots of open sets. And for each of them, you have the ring of smooth functions on UI. You have an opposite restriction maps in opposite direction. And then the germs are the same as inverse direct limit of C infinity of UI. It's probably easiest to see if you speak of analytic functions, because for complex analytic functions, if this UI were connected, these were all embeddings. We know that this is the principle of analytic continuation, that if you know the complex analytic function or real analytic function in small open set, you know it in bigger open set. So this is all embeddings, and this direct limit is a union. But in fact, this is really the best definition of germs, even not if it's not a union, because so if you have a we are interested again in maps from this set to our rings which are to a ring which are interested in. So we are interested the elements of this ring will be precisely the equivalence classes, because for each UI you can restrict it as a function to a smaller set and then take a quotient by these equivalences. So it's not hard to see that the direct limit of the smooth functions gives you the ring of germs. So people work with this direct and inverse limit all the time, even some of them don't know what it is. So today I'm interested in finite diagrams. In fact, only in very simple diagram. Namely two, there's no arrows, just two elements. So definition, consider a diagram. You have two elements, no arrows, C1 and C2. Okay, X1 and X2, where Xi are objects in category C. There are no arrows. Then the limit of this diagram is called product of x1, x2, and co-limit is called coproduct of x1 and x2. In other words, we have two objects, x1 and x2, and we have a third object, x. So if we're interested in maps from x to x1 and x2, so morphisms from x to this product is the same as product of morphisms from x to x1 multiplied by morphism from x to x2. This is another definition of product, which is not entirely clear that it is equivalent to that one, but it is. It's sort of clear that if you have an object which has this property, then it is a universal object for this like terminal object for this diagram, because if you have a map from x to there and x to there, this gives you a map from x to this object. So it is a terminal object. And then you can restrict it to this and to that, and you obtain. So you also, of course, need So if you have a map from x1 times x2 to these two guys, this map is called projection. So the product is a terminal object in the category of maps to x1 and to x2, which is the same as having this property. And this property is actually means that you know what, I mean, you know the corresponding functor to sets. So the product of x1 and x2 is represented, I mean, it's an object which represents this functor. So you have a functor, say f of x of a. It's equal to morphisms from a to x1 times morphisms from a to x2. It's a functor to sets. And we want this functor to be representable, and what this functor is represented by the product. So exercise, prove that product represents a functor or the functor. X goes to morphisms from x to x1 and times morphism from x to x2. And coproduct, of course, represents the opposite. It will be a functor x goes to morphism from x1 to x times x2 to x. Okay. So for instance, for sets, the product is really a product. So if you have a map from x to x1, you have max to x2, you have a map from x to a product of these two guys, and this is the same. For vector spaces, for topological spaces, this is all products. Because you can easily check that for to have a map from x1 times x2 is the same to have a map from x to x1 and a map from x to x2. This is the same notion. Okay, so it's really true that products are can be defined categorically. There are categories which admit products. There are categories which don't admit products, of course. Now, what about coproducts? So for coproducts, you want to have an opposite. So coproduct. You have morphisms. Let's denote it by x, y. This notation is inspired by, because for sets, the joint union is precisely coproduct. So we want to morphisms from x the joint union with y, coproduct to y to a, to be equal to morphisms from x to a multiplied by morphisms from y to a. Good. This is for sets, this is precisely what we need. For sets, this is precisely just the joint union of two sets. This has this property. So this implies that this if you have the diagram formed by these two sets, the set X and the set Y, and you are interested in maps to, say, A, this is precisely, I mean, every such map is factorized through the map from a disconnected disjoint union. This is why the disjoint union of two sets is precisely their coproduct. More interesting is this I mean, for vector spaces, it's just product. So for vector spaces, coproducts and products are the same. It's also very easy to see because if you have two vector spaces, you have a vector space to another, a map to another space. It's the same as the map from product from like direct sum of these two vector spaces to the same A. So tensor product doesn't occur so far. It will occur on the next slide. More interesting is what happens with groups. So product of groups, if you have a map from group to X1 and a group morphism from group X to X2, this is, of course, the same as a map to a product. So in the category of groups, products are the same as products. So what about coproducts? So you have, say, Z times Z. And you're interested in a map from these two copies of Z to some group G. Generally speaking, if you take an element in that Z and an element in this G, you put it to G, they would have a relation. Which is bad because this means that you would, not every map will, if you have some other map to G prime, and you have the map, different colored yellow map to G prime, typically there won't be any way to factorize that because the relation in G and the relation in G prime will be typically distinct. So if you want that to have a factorization, you want to prohibit all relations. This is what is called coproduct. It's called free product of two groups or free group. Here, if you take Z by Z, the coproduct, it's also called amalgam. It's a free group. Here we have two generators and no relations. And then from this free group, you have, since there are no relations, you have a map from every two group for any other two group where you have two maps from Z. So coproduct of groups is their amalgam. This is an important notion in group theory, yeah?
What is F2? Just
F2 is a free group of two generators. You have map from Z, map from Z. And for any other G prime, there is this factorization, which implies that it's precisely, so if you have, so what is maps from, morphisms from Z to G times morphisms from Z to G is you have a pair of elements in G. And if G is free, then this is the same as morphism from Z from F2, sorry, F2 to Z, from a free group. There are no relations in that group, so you can pick generators and map it to whatever you like here. So this is why you have this identification between these products, which gives you coproduct of groups. Okay. So far it was slightly, there was no tensor product, no algebraic geometry. It was just illustration of this interesting picture. So except for this coproduct of groups, everything was pretty much elementary. You can coproduct of spaces, or topological spaces, of sets is just the joint union. The product of them is a product. And for vector spaces, products are coproducts. For rings, it's slightly more interesting, so let's do it for rings. Oop. Yeah, before I go do rings, I should, I don't know, maybe I should skip to pair of slides and explain what about products and, well, I would just do it without slides. Right? Right. So what about coproducts for we know that the category of rings, reduced rings, is the same as category of algebraic varieties with opposite arrows. So coproducts in colimits, coproducts in reduced rings are the same as limits products of algebraic varieties. This sort of, because we know what is that the product of algebraic varieties corresponds to tensor product of rings, this suggests that a tensor product of rings should be a coproduct, and this is true. So claim coproduct of rings is their tensor product. Abelian groups are groups. No, for abelian groups it's the same as for vector spaces.
Yeah, so it's tensor
It's no, just product. There are no products for abelian groups because they are not models over a ring. Well, they are models over Z, but it's still false. Only for rings the coproduct is tensor product. For abelian groups, the coproduct is a product. It's like for vector spaces. Okay, so why it is so? We have map from A to something. We have two rings, A1 and A2. And we have maps from A1 and A2 to R. This obviously gives us a map from A1 times A2 to R. Because we can just multiply, we can embed A to tensor product, A2 to tensor product, and this will give us, so if you have multiplicative map from A1 to R, from A2 to R, this would give you a map from tensor product to R. But the converse is also true. Say, let's multiply over C, for instance. So suppose it was all rings over C. Then A1 times sits there. So you have, here you have two subrings, A1 times C and times 1. Well, times C times 1 doesn't matter. And you have another subring, which is 1 times A2. And they are both mapped to R. So indeed, pair of maps from A1 to R and A2 to R are the same as maps from the tensor product to R. This is one-to-one correspondence. So this is why it is coproduct. And if you want a product of rings, it's much less interesting. So product of rings is just A1 times A2 is direct sum. And of course, this, if you think about direct sum, you will realize that the direct sum corresponds to disconnected union of two algebraic varieties. And coproduct of algebraic varieties is disconnected union. So this is very natural from the categorical point of view. Okay. So I'm almost done with categories. Now let's return to what we had last time. So I'm showing you the slide, which we had last time. So I won't give the proof probably, unless you want me. But at least I would repeat the statement. So claim 2. It's about tensor product and preimages. So you have f from x to y map of algebraic varieties, morphism of affine varieties. You have f star from OY to OX. It's homomorphic regular functions. Then I have z. Z inside Y subvariety. We're interested in its preimage as subvariety. Well, its preimage obviously algebraic because the Z is given by polynomial equations, F is given by polynomial maps, so preimage of this Z is also given by polynomial equations, just composition of F and that equations. But what about rings? So we can define it also in the language of rings. So suppose that IZ is this ideal. It's inside OY ideal. Then we have a R1 is a quotient of OX multiplied tensor over OY. OY is a sits in, well, it's mapped to OX, so it's natural to consider OX as a model over OY, and multiplied by OY quotient by IZ, and we take this quotient by need radical. Then preimage of Z is spectrum, so it's a subvariety, is variety associated with R1. And the proof is, as always, Hilbert-Neustein ansatz, because proof we consider an ideal IZ multiplied over I OY OX is ideal in OX, and it is an ideal so it's radical is an ideal of f minus 1 of z. Clearly, all functions from this ideal vanish in this preimage because they vanish. I mean, these pullbacks of functions on y, which vanish in z. Conversely, if you have a function which, if you have a point x in x which doesn't map to, if you have x such that f of x is not equal, doesn't belong to z, then you have a function on y which vanishes on z and doesn't vanish in that image, and its preimage will belong to this ideal, but it won't belong to, it won't vanish on this point x. So this means that the f minus 1 of z is the set of zeros of this ideal. And then we apply Hilbert-Neustein ansatz, which tells us that if you have an ideal, its common zeros are certain variety, like f minus 1 of z, then its radical is the ideal of this variety. So this is claim 1, claim 2, sorry, claim 3. The enumeration is because we had it in the previous lecture. I just repeat this slide because last time we're out of time and it was slightly too fast. Okay, claim 3. You have a diagonal inside m times m is diagonal. that is a set of all x, of all pairs, x inside m times n. Now you have an ideal r times 1 plus r1 times r plus 1 times, or sorry, r times 1 minus 1 times r, generate ideal. So then generate ideal of diagonal. Proof? Well, clearly such functions vanish in the diagonal. It's clear. On the other hand, if you have a function which, yeah, and the quotient, so if you have O of m times O of m over c, and you take this quotient by this ideal, let's call it I. This is the same as O of m times O of m over O of m, because this is bilinearity ideal. So this is O of m. This has no z divisors. So it's a radical ideal, and it's sufficient to prove that this is an ideal of diagonal. It suffices to show that its set of zeros is diagonal. Okay, we already know that any element in diagonal is 0 of this ideal I. And conversely, if you have a point which is not in zeros, m prime, like here, you take a function f which vanishes in m and doesn't vanish in m prime. Such function exists. And then you put f times 1 minus 1 times f, and it doesn't vanish in m prime. So this means that every point which is off diagonal is not in the zero set of this ideal. So we have the zero set of this ideal is diagonal. Make clear? I'm just repeating, so I'm doing slightly faster than I should, but if it's clear, Yulia, is it clear? Mm-hmm. Yeah, I am too fast, so I should slow and maybe repeat even. So I can write down at least the argument if it's too fast. Okay, so step 1, it implies that then I is radical. So I is the square root of I. I mean, I is the radical of I. Okay, so step 2, by Neustein Satz, it suffices to show that diagonal is a set of common zeros, is annihilator of I. Well, first, if m, so if you have function 1 minus times r minus r times 1, and you evaluate it at so this means that you plug here and there, and this will be the same. So this is 0. On the other hand, 1 times f minus f times 1 evaluated at m prime is non-zero if f of m is equal 0 and f of m prime is not 0. So this point is not an annihilator of I, and this point is an annihilator of I. So this implies that common zero set of this ideal is diagonal, and we can apply Hilbert-Neustein Satz because we already proved that this is a radical ideal. Okay, let's use it. Yeah, so fiber product is a product, but it's a product in relative situation. So if you have two varieties which are mapped to a third variety, Grudnik would call it variety over a variety. So definition, if you have f from x to z, is it z here? To n. To n, and z from y to n, then x times y over n is set of all points x and y such that f of x is equal to g of y. So this is the same as f times g minus 1 of diagonal, where f times g is a map from x times y to m times n. It's a product of these two maps. So this is, you can do it in topological situation for sets, or you can do it for algebraic varieties. It will work because this is a preimage of algebraic set. And we already know that preimage of algebraic set is algebraic. So this is well defined. Now I'm going to interpret this fiber product in terms of tensor product. Yeah, here it was pi x and not f. So let me state this claim with pi x. So you have pi x from x to m, pi y from x to m. It's a morphism of morphisms of affine varieties. And then you have R1, which is O x multiplied over OM by OY. This makes sense because you have an inverse maps of rings, pullbacks, of algebra, of regular functions. So OX and OY are models over OM. You can take tensor product. And you take it again quotient by near radical. Then spectrum of R1 is equal to this fiber product, x times y over m. Okay, so it follows from two claims, which is that claim and this claim. So proof, and it follows almost directly, because what we know is that x times over m y is equal to preimage of diagonal pi x times pi y minus 1 of diagonal. Now diagonal is given by the ideal. Now we can apply claim 1, which tells us that the corresponding ring of regular functions is equal to the product or x times y over c taken by the radical of the ideal generated by this by the ideal of the diagonal in this so this map is mapped from x times so you have pi 1 times pi x times pi y. It's a map from x times y to m times m. Here you have diagonal, and we consider preimage of diagonal, so it's the square root of the ideal of diagonal. lifted to, so it's like pullback of the ideal of diagonal. Pi x times pi y of I diagonal. Okay, and now we know what is an ideal of diagonal by claim 3. So the ideal of diagonal is generated by elements. So you have OM, OX times OY, quotient by the ideal of form M times 1 minus 1 times M. This over C, this is where M belongs to OM. And this precisely OX times OY multiplied tensor over OM, because this linearity with respect to OM. So this is equal to OX multiplied by OY over OM, quotient by near radical. You have to kill all nilpotents here and there and there. Okay, we finished the proof. So this expresses the tensor product, well, the fiber product in terms of the tensor product. But there is another argument which is probably better. So first, product of algebraic varieties is product in the category of algebraic varieties. So I give it as a chain of exercises because we are out of time and because it's a good exercise. It's good exercises. I think next time I would convert it to a sheet of exercises which I would put on the page of the course. So exercise. So you have A, B algebraic varieties. Then A times B in category is equal to A times B as product, as a product of varieties. So the categorical definition of a product and the definition in which we always use, like just Cartesian product, are the same. And the proof is pretty obvious because if you have X to A, you have a map from X to Y, to B. This gives you a map from X to A times B, just set theoretically. But then this set theoretical map is by definition polynomial, so it's really algebraic map. So there's as many maps from X, algebraic maps from X to A for X to B as maps from X to A to B. So this is one-to-one correspondence. Okay, and we already discussed that coproduct of rings is tensor product. This is also elementary. Yes, there's nothing to prove essentially. I told you the proof, but it's almost straightforward. Okay, it was for rings, but now we are interested in the category of reduced rings. So we want to have a reduced ring, and the claim is another exercise. But it's proven is directly the same as previous. So if you have A, B rings with no nilpotents, then you can take coproduct of A and B in category of reduced rings. Reduced is no nilpotents. Rings is the same as their product, tensor product, by near radical. What does it mean? Well, I can easily explain. So you have a map A and B. We're interested in the map to R. Of course, this gives you a map from tensor product, like previous time, A multiplied by B to R. But R has no nilpotence. So this map is factorized through a quotient by new radical. It's uniquely factorized through quotient to new radical. So there are as many maps from this tensor product to R as the maps from this quotient to by new radical to R. So this implies this statement about tensor product. Okay, and this immediately gives a theorem which I already had, but now the proof is for free. You don't do anything. So last time we did something to prove it. Now it's immediate, like nothing to do. So spectrum of A times B by any radical is a spectrum of A times spectrum of B. This is because the category of rings is equivalent to opposite category to rings is equivalent to algebraic varieties. The product of algebraic varieties corresponds to coproduct of rings, and we just shown that coproducts of rings is quotient by any radical. Okay, I'm almost done. This is the last slide. It interprets the fiber product in categorical terms. So definition. You have a diagram in category A and B goes to C. A, B goes to C. This is one diagram, and the fiber product in category is limit of this diagram. And it is almost clear that it is indeed the, for instance, for topological spaces, for algebraic varieties, the fiber product of this, or for sets, the fiber product will be limit of this diagram. It's the same as we just discussed when C doesn't exist. The proof is entirely, literally the same. And of course, you can define coproduct. You take opposite diagram and you do opposite arrows. Co-limit instead of limit. So definition, if you have C goes to A and B, coproduct, co-limit of this diagram, is the same as fibered coproduct. Co-fibered coproduct. Co-fibered coproduct. I think if you say fibered coproduct, it would be the same. At some point, people stop caring about co, and they just forget it. OK. Now you use the same argument, and you notice that a coproduct, if you have two rings, like C sits inside, maps inside A, so example. This is a very good notion, by the way, for the groups. It's called if you do coproduct in that situation, it's called amalgam of two groups over C, and it's really useful in group theory. So but we're interested in rings, so if you have C maps to A, C maps to B, is ring homomorphism, then tensor product A times B over C is coproduct is fibered coproduct. It's co-fibered coproduct. Co-fibered coproduct. It's the same. You just, instead of having this kind of maps, you have the same maps, but over, which are C-linear, like over C. And the argument is the same. Okay. And this gives you immediately, because we already know about products, fiber products of algebraic varieties, this gives you a useful claim after you do these exercises, which are one line. So claim, which is a corollary from all these identifications and very simple definitions, that if you have a x and y, they are both fibered mapped to M, algebraic, well, affine. Then x multiplied over M by y is the same as spectrum of x of OX tensor product over OM by OY quotient by any radical. This is because this category are equivalent up to inverting arrows. This is fibered product, this co-fibered coproduct of the same objects. Yeah, this is actually an example of what Grundig realized. Well, he always said that is his main lesson that he learned in math, that if you do correct definitions, all theorems becomes trivial. And this is the ideal, for Grundig, this was the ideal situation in math, when you start from good definitions and you don't need to prove anything. This is why he, for instance, didn't like the proof of Weyl conjectures that Deligne did, because it's non-elementary, and he believed that if you do good setup, you do correct definitions, then it will be simple as this proof. Okay, I'm done. Thank you very much. Muito obrigado.